All right, the next part about astrophysics is about Doppler shift, the Doppler effect, and the expansion of the universe, and how do we figure out stuff like that. So here's the first equation. It says that, remember the Doppler effect? If something is like sound, like when something's moving, wavelengths and frequency can shift. It can appear to be something different than what it actually is. Light does the same thing. So if something's moving towards you, the wavelength of light is going to get smaller, making it blue shifted, it's called, because the wavelength is going to appear a little smaller than what it actually is. And since it's moving away from you, it's going to make it red shifted, move towards the red spectrum, because the wavelength is going to get a little bit longer as it moves away from you. So it turns out that we can actually do some calculations with that. So the change in wavelength, how much the wavelength is actually changing, is on top. The actual wavelength, what it actually would be if it wasn't moving, is on the bottom. So that ratio is equal to the ratio of v, which is the speed of the star. How fast is the star moving relative to us over the speed of light? Because that's what we're detecting is the speed of light. Remember, the speed of light is 3 times 10 to the 8th meters per second. So in order to see any shift of color at all, these stars seem to be moving pretty fast relative to us. Now, here's the first, before I talk about the next section, the next equation, let's go over spectral lines. So remember, spectral lines are produced by, known elements. So if I look at hydrogen, the most abundant element in the universe, stars are mostly made up of hydrogen that's fused together. If you look at the spectral lines of hydrogen, these are just totally made up numbers that are made up. But let's say that hydrogen looks like this, has a spectral line energy level at 500 nanometers, 600 nanometers, 700 nanometers. Those makes 3 lines, and those exact wavelengths of light are being emitted from hydrogen. Then I look at a star, and I see its spectral lines, and it has 510, 610, 710. So right away I know, you know what, that's pretty close to hydrogen. It matches up really well, and they're all the same, they're all 10 nanometers off of hydrogen. So, you know what, that matches up pretty well with what it should be. Now these are rounded numbers, so they're not exact, and these are made up, by the way, so don't use this, but this is an example. So, not only did it tell me what the star is made of, but I can also get information about what the star is doing. So let's calculate the speed of the star. So I know it's made up of hydrogen because all of these match up really closely to what hydrogen is. So I know it's made up of hydrogen. Calculate the speed of the star. Well, I'm going to use this equation here. Just the right side of the equation. We'll talk about what z is in a bit. So calculate the speed of the star. So delta wavelengths. Let's pick out the first one. The change in wavelength is 10, because it went from 500 to 510. The actual wavelength is 500, equals c, which is the speed of light that goes on the bottom, 3 times 10 to the 8th meters per second. And then I calculate how fast is the star moving. So let's do that. 10 over 500, and then I would have to multiply by the speed of light, 3 times 10 to the 8th, and this is 6 times 10 to the 1, 2, 3, 4, 5, 6 meters per second. 6 million meters per second. Or another way to say this is 6,000 kilometers per second. So every second it's moving 6,000 kilometers. That's insane. Now, let's talk about the next part of the equation, z. Z is like a scale factor. It's the redshift factor. How much is it redshifted? So if you, there's a guy named Hubble that looked at the night sky and did a bunch of the Hubble telescope. He looked at the night sky and he did this for a bunch of different objects in the sky, and he found out that like 90% of the objects in the sky are all redshifted. They're not blue shifted. There's only a couple random objects that are blue shifted moving towards us, meaning that most of the objects are red shifted. And the farther out that he looked, the more and more red shifted they were. So we'll talk about that in a second. But basically, since most of the stuff was red shifted, he's like, you know what? Maybe everything's, for the most part, moving away from us. So hence the Big Bang Theory was kind of thought of. Like everything's moving away from us, so everything's expanding. And the farther out you get, the faster it's expanding. So it's like everything's expanding faster and faster and faster the farther out you get. So that's what this graph looks like. He looked at a bunch of different objects, that's what these points are, and he measured the velocity of them, or calculated the velocity using this equation, in kilometers per second, and measured the distance using the distance things that we talked about before in megaparsecs, or millions of parsecs. So as the distance increased, the velocity increased, meaning that the things that were farther away from us were moving faster, and faster and faster and faster, until basically there's to a point where we couldn't even see things anymore because, one, they're so far away, and two, they're moving away from us so fast that by the time we see it, the light's already, it's moving close to the speed of light. You know, it can't reach the speed of light, but it can get close. So it's crazy. So we can calculate that z factor just by taking that ratio. So 10 over 500 tells us that z is 0.12. And it's just a number. And the bigger the number this is, the more redshifted it is. So this is always going to be a positive number less than 1. Okay, so we already talked about this. Most things are redshifted. What can you conclude about this? Well, you can't conclude anything, but you can make an assumption saying that, well, you can conclude that the universe is moving away from us. And one theory that was arose from that was the Big Bang theory. It says, well, if we look backwards then, that means that everything was been, at some point, close together. And if you work backwards, maybe it started as one small point in space, and then that point exploded, and everything just expanded out at increasing rates, apparently. So that's the idea of the Big Bang theory. So we're going to talk about the second equation here in a bit, but that's how you can use spectral lines, like spectroscopy, like clever optics, to figure out what stars are made of and what they're doing. Are they moving away from us, towards us, and how fast? Now, going back to Hubble, he made some information, or grasped some information about this, velocity in kilometers per second and distance, and he found the slope of this graph. And it's literally, like, it's a perfect slope. It's like unbelievably perfect. And he found out the Hubble Constant, labeled as H naught or H0, or sometimes just labeled as H, the Hubble Constant. And the slope of this graph is 72, and the units would be kilometers per second per megaparsec. So those are kind of weird units. But what we can do with that is we can actually figure out how old the universe is. So let's go through that. We're going to use, we're just kind of break down what these units are. Let's get into units that make sense. 72 kilometers per second per megaparsec. That's really crazy. So let's break down the units a little bit. Now, let's first convert this to meters per second. 72 kilometers per second is 72,000 meters per second. Okay, we still have to develop the megaparsec thing. Now, what's a parsec? Well, what's a megaparsec? A megaparsec is 1,000,000 parsecs. So let's do that. Let's put down 1,000,000 parsecs. PC. Well, how big is a parsec? Well, one parsec is equal to, remember when we did this when we did distance calculations, is 3.1 times 10 to the 16th meters. So if I do 1,000,000 times this, I get 3.1 times 10 to the 22 meters. So we're taking meters, some number of meters per second divided by meters. The meters cancels out. So we're left with a unit of 1 over seconds, or like inverse seconds, essentially, which is still a weird unit, but it's more, it's getting closer. Let's actually get a number for that, though. So 72,000 divided by 3.1 times 10 to the 22. So Hubble's constant simplifies to 2.3 times 10 to the minus 18th seconds to the minus 1. Now, here's where this equation comes in. T. T is the age of the universe, the amount of time, based on the slope. If we trace it backwards, when the velocity was 0, when things weren't moving, at a distance of 0, meaning that there's no space, a finite space, 0, 0 is the beginning of the universe, where everything was compressed into a finite space and time was 0. So we can use that slope to figure out a point 0, 0 essentially, and how old the universe is in seconds using this equation. So if I do 1 divided by that number, the age of the universe in seconds, 1 over Hubble's constant will tell me that number. Because if I take 1 over seconds, I just get seconds. So if I do 1 over that number, I get the age of the universe is 4.3 times 10 to the 17th seconds. Well, let's convert it to something a little more reasonable. So let's divide by 3,600. That gets us to hours. Then we'll divide by 24. That gets us to days. Then we'll divide by 365.25. It gets us to years. Okay, so now we're left just 1.36 times 10 to the 10th years. Or another way to say that is 13.6 billion years. Because if I divide by a billion, I'm left with 13.6 as an answer. 13.6 billion years is the theoretical age. Now there's a little bit of uncertainty in that measurement. Oh, maybe there's a lot. I don't know. I think the accepted value is 13.8 billion right now, but that's how we get there. And so what's crazy to think about is that by looking at spectral lines of bright dots in the sky, we can figure out what they're made of because they're really close to what atoms are, like really, really close. And then we can also figure out, as we look farther and farther using the parallax method, farther and farther into space, we find out that things are moving faster and faster and faster away from us. So it's almost like a bomb went off a long time ago and things are just expanding and it's getting more and more expansive. So that's the idea of dark matter. Dark matter is kind of like this dark energy and dark matter are kind of like these visible forces and stuff that we can't detect, but we know based off of how much matter and stuff should be in the universe, there's something there that's like repelling everything, making it accelerate upwards. That's the dark energy aspect. And dark matter could be causing that dark energy to happen. So it's very, very weird to think about. And it's something that we're trying to find more about because maybe there's some sort of useful energy there that we could utilize. Or maybe it's dangerous, I don't know. But it's very, very interesting. This to me blows me away in how that's crazy, how linear that was. But so once again, there's the next topic. We have one more topic left for astrophysics, so stay tuned.